Hello, in this video we will investigate two inverters cascaded. So here you see one and here you see the second one. In this example, the PMOSes are identical and NMOSes are identical. Here we have this connection. Two inverters are cascaded and we are looking at value of V out. So this is an easy case, but what happens if there's some noise at this point? We can represent the noise for this example with an RF here. So let's take this RF value as 10 kilo ohms for now. We can investigate this example with two cases. First, when V in is equal to 0. Then this NMOS here will be off. Why? Because whatever this point, let's call it Vx, whatever this point's voltage is, since the gate voltage of this NMOS is 0, it won't be conducting. Let's draw the new circuits with NMOS off. So we have this PMOS and 0 volt at V in, 0 volt at gate. We have this RF here and this is connected to the gate voltage of the second PMOS and gate voltage of the second NMOS. In this case, this point's voltage is VDD and here Vx, and in this loop current is 0. Why? Because if there's a current here on RF, it means Vx is smaller than VDD. In that case, there is no current in this direction in this NMOS. So this loop current here is 0. Then, since there is no current flow through this unwanted resistance here, Vx is equal to VDD. When input of the second inverter is VDD, then V out is 0. So as you see, RF didn't affect the function of these two gates. Let's look at the second case, when V in is equal to VDD. Then this PMOS here will be off. We can draw the equivalent circuit with RF connected to NMOS and NMOS gate is connected to V in, and that is equal to VDD. After this point, we have another inverter. Here we are looking for V out. As you can see, we have a familiar structure here. We have a resistor load inverter with an input VDD. So what happens when the input of a resistor load inverter is high? Output of this inverter will be VOL. We can calculate VOL using this formula, VDD minus Vt0 of NMOS plus 1 by Kn R. Load resistance here is Rf minus square root of VDD minus Vt0 of N plus 1 by Kn Rf squared minus 2 VDD divided by Kn Rf. So if we use this formula, VOL can be found by 3.3 minus 0.7 plus 1 by 500 micro 10K minus 3.3 minus 0.7 plus 1 by 500 micro times 10K square minus 2 times 3.3 divided by 500 micro 10K. And this is equal to VOL 0.246 volts. So if you look at these values, Kn is equal to Kp and Vt0 of N is equal to absolute value of Vt0 of PMOS. That means these inverters are symmetrical inverters. Ideally, we have to calculate VIL of the second inverter, but I'm not going to do that because I know this is a symmetrical inverter and VTH is 3.3 divided by 2, that is 1.65 volts, and when we compare these two values, ideally VOL should be this 0.246 volts. VOL of resistor load inverter should be smaller than VIL of the CMOS inverter to see a high value at the output. And here, if you calculate VIL, you will see that it is far above this value VOL here. So we can say that there is a logic 0 at the input of the second inverter, so output of the second inverter will be logic high. And logic high means VOH for this CMOS inverter, and that is equal to VDD.